Hello everyone, welcome you all on my YouTube channel Tesla tutorial. Dear students, in this video we are going to discuss about compound microscope. So first of all, let's see the construction of the compound microscope. So a compound microscope consists of two convex lenses mounted coaxially within two sliding tubes. The distance between these two lenses can be arranged with the help of rack and pinion arrangement. Out of these two lenses, one has short focal length as well as short aperture and a facing object AB called objective, while other has larger aperture and large focal length and near to the eye called eyepiece. This is all about the construction. Now let's discuss about working principle. So working principle is very simple. First, whatever is the object placed in front of the objective gets magnified with the objective, and then this magnified object works as magnified image actually of the objective, works as object for the eyepiece, and again gets magnified up to large extent and appears as final image A double dash B double dash formed by compound microscope. This is all about the working principle. Now let's talk about the magnifying power or angular magnification of the compound microscope. So as in case of a simple microscope, we define angular magnification. The same way here we are going to define. So if we write the definition of the angular magnification, then simply we can say it is the ratio of the angle subtended by the final image A double dash B double dash to the eye when seen through the compound microscope to the angle subtended by the object AB when seen directly, while both final image A double dash B double dash and object AB are lying at least a distance of distinct vision, that is of 25 centimeter length. So this is all about the definition of angular magnification. If we write mathematically the same thing, then we can write m is equals beta upon alpha. So here you can see beta is the angle subtended by the final image A double dash B double dash to the eyepiece. As eye is very close to the eyepiece, so whatever is the angle subtended by the final image A double dash B double dash to the eyepiece is the angle to the eye as well. So if you're talking about alpha, then alpha here AB is the object which is now situated at least distance of distinct vision. Here with respect to this, you can see this AB is lying in the line of A double dash B double dash. So AB is now on the least distance of distinct vision, at least distance of distinct vision. So in this way, AB is subtending angle alpha to the eyepiece as well as to the eye. So this is the alpha. In practice, actual alpha and beta both are very small angles. So in that case, by mathematical approximation, we can write m is equals tan beta upon tan alpha. If you are talking about tan beta in the right angle triangle O A double dash B double dash, then simply we can write tan beta equals A double dash B double dash upon O A double dash. That is O A double dash, that is least distance of distinct vision, capital D. And if you are talking about alpha, then we can write tan alpha, then we can write tan alpha is equals AB upon OA, that is D. So AB upon D, here D and D cancels each other, and this equation capital M is equals means total angular magnification reduces to A double dash B double dash upon AB. This A double dash B double dash can be arranged like this by multiplying and dividing A dash B dash to the equation as we can write A dash B dash upon AB into A double dash B double dash upon A dash B dash, which is equivalent to this. Why we are writing actually this? Because A dash B dash upon AB is the magnification produced by objective, while A double dash B double dash upon A dash B dash is the magnification produced by eyepiece. So in this way, total magnification is equal to the product of magnification produced by objective and eyepiece. And here clearly you can see here in the figure, a double dash b double dash is the height of image for the objective, while ab is the height of object for the objective, and a double dash b double dash is the height of the image for the eyepiece, and a dash b dash is the height of the object for the eyepiece. So in this way we can write hold this value to mo into me. Now we have to get the value of magnification of mo and me in terms of known values v0, u0, and ue and fe. So let's have these values, means magnification produced by objective and eyepiece in terms of ue, ve, fe, and least distance of distinct vision d. So if we are doing the same thing, then we can write magnification produced by objective is equals v0 upon u0, and magnification produced by eyepiece ve upon ue. Here v is equal to d, while ue is equals oa dash. Here oa dash is the distance of the image, distance of the object actually for the eyepiece. So this is no more needed in the expression for the magnification by compound microscope. So we are going to replace oa dash with other known quantities. So the known quantities are actually focal length of the eyepiece, and this can be done by using lens formula. So for the lens formula, we can write 1 upon f is equals, for the eyepiece we can write 1 upon f is equals minus 1 upon u plus 1 upon ve. Here if we are applying sign convention and putting the value, then actually ue is equal to oa dash, because oa dash is virtual object, and ve is the ve is equivalent to minus d because the final image, means the image produced by eyepiece, is virtual as well. So in this way also you can say you are measuring these distance oa dash and oa double dash along negative x-axis, that is to the left of the optical center of the eyepiece. So in this way these values are taken negative, and if we are solving this, then we can write 1 upon fe is equals o1 upon oa dash minus 1 upon d. Here you can see 1 upon fe is equals 1 upon oa dash minus 1 upon d. If we are multiplying the whole equation by d, why we are doing so? Because we are having d upon oa dash as the magnification by the eyepiece. That's why we are multiplying this whole equation by d. If we are multiplying, then we are having d upon f is equals d upon oa dash minus 1. If we are arranging these the terms, then we can have magnification me which is equals d upon oa dash equals d upon fe plus 1. Now if we put the value of mo and me in the equation 1, then we can have total magnification v0 upon u0 plus 1 upon plus 1 plus d upon fe. Now this is the formula for the magnification when final image is formed at least distance of distinct vision. In case if the final image is formed at infinity, that is the image formed by objective, which is a dash b dash, lying at the focus of the eyepiece. In that case final image is formed at infinity, and if we are putting ve equals infinity, then in the lens equation, that means lens equation for the eyepiece, we can have d is equals fe. Clearly you can see in the solution where you wrote the equation, lens equation for the eyepiece. So in this way we can have me is equals d upon fe. So the final magnification m is equals mo into me, which is equals v0 upon u0 into d upon fe. This expression, means this formula, is okay when we are talking about final image at infinity, but this is applicable when final image is as at least distance of distinct vision. So that's it in case of compound microscope. Dear students, please watch this video and subscribe my channel, like the video also. Thank you.